Welcome back to the channel. Oh, this is actually wrong. Oops. This should be episode 35. Okay. I just woke up, so my voice is kind of interesting. Welcome back to the channel. It's been a while since I've uploaded. I've been pretty busy with my last year at university. So just a quick life update. I'm finishing up university, and I recently landed myself my first full-time IT role, and I'm really happy. It's big. It is a good offer. Nothing super crazy, but definitely a very good starting point. Um, so on Monday, I started work as a business analyst, and I just want to share this news with anyone that watches my videos because, you know, I started this channel not too long ago when I lost my part-time job working at a little food shop. And yeah, if you're a long time subscriber, you would have known that I didn't do just math on this channel. Um, I was doing programming, I was doing web dev, I was doing business intelligence and stuff. And I'm really happy that the hard work's paid off. A lot of people see this stuff and they think it's kind of pointless, but when I went into the interview and I talked about my body of work, it wasn't pointless. It was very, very purposeful. I was able to talk about web scraping. I was able to talk about certifications that I've done on this channel. I've showed my track record that I regularly upskill and improve with math and stuff. And I'm not a godsend by any means. I'm very subpar. I'm from New Zealand, so I think it's just very chill here. But you go to America and you go to these big tech cities, or you go to Asia, and then you go to these places like China and Hong Kong and stuff, and the kids there are just smashing it. They just know what the fuck they're doing. So what I'm trying to say is that you don't need to be a god, you just need to be interested and you need to be consistent. Because being interested for a day or a week or a month, it doesn't suffice. It needs to kind of be a long time, lifelong vision for you. So, yeah, let's just get started anyways. Thank you for listening to my TED Talk. Okay, session agenda, Unit 11, Inference or Quantitative Data Means. So, and I just want to share another thing. Recently, recently I had a statistics exam, and this statistics paper that I've been taking has covered, just happens to have covered so many of the things that we've been going through these past couple weeks, past couple months. And this paper, I didn't even have to study for it because I just do math in my spare time, which is kind of crazy to me. Okay. Confidence intervals, we know what those are. They're essentially the hit rate in which when you generate a confidence interval, oh God, it's been a while, um, that you're able to actually capture the true population mean, or any parameter for that case. Okay, so setting up t-test, not t-test, setting up a test, carrying out a test, confidence intervals for two different means. Okay, and I will not be pausing the video even for breaks today because I usually do, but I'm tight on time and I've been putting off the math videos as of late. So if I need to use a break or have a coffee break or whatever, I'll just be in the background chatting. Yeah, yeah. Which sample satisfied? Oh, wait, hold on. Yep. Okay, let's start.
bottles in the batch. So that's
Okay, Sal is going to talk about t statistics and why we should use t statistics over z statistics at times. So the t and z distribution are both using the normal distribution, but the t statistic is narrower, I think. It has a higher peak. Oh no. it's water, other way around. And we use a t-statistic when we don't have population standard deviation, and when our sample sizes are not big enough, I think. I think that might be it.
Z table. We have already seen a situation multiple times where there's some parameter associated with a population. Maybe it's the proportion of a population that supports a candidate. Maybe it's the mean of a population, the mean height of all the people in the city. And we've determined that it's unpractical, or there's no way for us to know the true population parameter, but we could try to estimate it by taking a sample size. So we take n samples, and then we calculate a statistic
1.5.
based on
That's
that.
fine.
We've also seen that not only can we calculate the statistic, which is trying to estimate this parameter, but we can construct a confidence interval about that statistic based on some confidence level. And so that confidence interval would look something like this. It would be the value of the statistic that we have.
Confidence interval, confidence level, not the same thing, but related. So you need a confidence level to know how to generate a confidence interval.
Just calculated, plus
I
or
say
minus some
interval,
margin of
interval.
error. And so we'll often say this critical value, z,
Yep.
and this will be based on the number of standard deviations we want to go above and below that statistic. And so then we'll multiply that times the standard deviation of the sampling distribution for that statistic. Now, what we'll see is we often don't know this. To know this, you oftentimes even need to know this parameter.
So we
For
use
example, in a situation where the
estimator.
parameter that we're trying to estimate and construct confidence intervals for is, say, the population proportion. What percentage of the population supports a certain candidate? Well, in that world, the statistic is the sample proportion. So we would have the sample proportion plus or minus z star times, well, we can't calculate this unless we know the population proportion. So instead, we estimate this with the standard error of the statistic, which in this case is p hat times 1 minus p hat, the sample proportion times 1 minus the sample proportion over our sample size. If the parameter we're trying to estimate is the population mean, then our statistic is going to be the sample mean. So in that scenario, we are going to be looking at our statistic is our sample mean plus or minus z star. Now, if
Guys, this video is going to be kind of a weird one. It's going to be, chill. Sometimes I do this. I'm usually pretty good though, I promise, but just because I got the have to multitask a bit, I'm going to be looking at like baking recipes and stuff because I have dinner with my girlfriend's family tonight and yeah.
we knew the standard deviation of this population, we would know what the standard deviation of the sampling distribution of our statistic is.
This is the
It would
one.
be equal to the standard deviation of our population times the square root of our sample size. But we often will not know this. In fact, it's very unusual to know this. And so sometimes you will say, okay, if we don't know this, let's just figure out the sample standard deviation of our sample here. So instead, we'll say, okay, let's take our sample mean plus or minus z star times the sample standard deviation of our sample, which we can calculate,
Coconut oil.
divided by the square root of n. Now, this might seem pretty good if we're trying to construct a confidence interval for our sample, for our mean, but it turns out that this is not so good. Because it turns out that this right over here is going to actually underestimate the actual interval, the true margin of error you need for your confidence level. And so that's why, so instead we'll say, okay, let's take our sample mean plus or minus z star times the sample standard deviation of our sample, which we can calculate, divided by the square root of n. Now, this might seem pretty good if we're trying to construct a confidence interval for our sample, for our mean, but it turns out that this is not so good. Because it turns out that this right over here is going to actually underestimate the actual interval, the true margin of error you need for your confidence level. And so that's why statisticians have invented another statistic. Instead of using z, they call it t. Instead of using a z table, they use a t table. And we're going to see this in future videos. And so if you are actually trying to construct a confidence interval for a sample mean, and you don't know the true standard deviation of your population, which is normally the case, instead of doing this, what we're going to do is we're going to take our sample mean plus or minus, and our critical value, we'll call that t star, times our sample standard deviation, which we can calculate, divided by the square root of n. And so the real functional difference is that this actually is going to give us the confidence interval that actually has the level of confidence that we want. If we want a 95% level of confidence, if we keep computing this over and over again for multiple samples, that roughly 95% of the time, this interval will contain our true population mean. And to functionally do it, and we'll do it in future videos, you really just have to look up a t table instead of a z table.
Yeah, let's watch the next one and see why. I think he's gonna show the hit rate here. Hmm. Come on.
In future videos. In a previous video, we talked about trying to estimate a population mean with a sample mean, and then constructing a confidence interval about that sample mean. And we talked about different scenarios. We could use a z-table plus the true population standard deviation, and that actually would construct pretty valid confidence intervals. But the problem is you don't know the population standard deviation. And so you might try to use a z-table to find your critical values plus the sample standard deviation. But what we talked about is that this doesn't actually do a good job of calculating our confidence intervals. And we're going to see that experimentally in a few seconds. And so instead, we have something called a t-statistic, where if we want our critical value, we use a t-table instead of a z-table. And then we use that in conjunction with our sample standard deviation. And then all of a sudden, we are actually going to have pretty good confidence intervals. To make this a little bit more real, let's look at a simulation. So this is a scratch pad on Khan Academy made by Khan Academy user Charlotte Owen. And the whole point there is to see what our confidence intervals look like with these different scenarios. So let's say we have a true population mean of 2.0 for some, let's say it's the average number, the mean number of apples people eat a day. The true population mean is 2. That seems high, but maybe it's in a certain country that has a lot of apples. And let's say we know that the population standard deviation is 0.5. And we're going to create confidence intervals with a goal of having a 95% confidence level. And we're going to take sample sizes of 12. So first, we can construct our confidence intervals using z and sigma, which is a legitimate way to do it. And so let's just draw a bunch of samples here. And so we do see that it looks like it is roughly 95% when we keep
Z with sigma means that you're doing a Z distribution. You're doing a Z test. No, not Z test. You're generating a confidence interval with the Z table. Okay? So with a Z score instead of a T score, plus minus Z star. And sigma means that we have the population standard deviation, which he mentioned is unusual to have, not very common. And okay. Yep,
making
okay.
these samples and constructing these confidence intervals, that 95% of
Roughly
the time,
95%.
these confidence intervals contain our true population mean. So these look like
95% of the time. This is standard error.
good confidence intervals. But what we talked about is normally when you're doing this type of thing, this type of inferential statistics, you don't know the population standard deviation. You don't know sigma. So instead, you might be tempted to use z with our sample standard deviations. But if you look
Oh yes, and just remembering that you draw samples, then you do the confidence interval. Yes, okay.
at that for these exact same
And the confidence interval is based on a sample. So when you draw samples and you generate a confidence interval, that I see. Okay.
samples we just calculated, notice now when we did
Sometimes it takes some time to sometimes it takes a bit of back and forth, maybe over a couple of sessions, maybe over one session, maybe a few months, to really let things sink in. So each confidence interval is using the same formula, is using the same calculations, same critical z value, but the sample changes. The set of 25. Every time every time, oh well, not set of 25, set of 12. So each bar here has a sample size of 12, so there were 12 samples, no, 12, 12 elements in a sample, 12 objects. And sometimes he gets 12 from here, 12 from here, maybe 12 from here and here. Okay.
Over and over again. We've done this 625 times. In this scenario, where we keep calculating the confidence intervals with z and s, the true population mean is contained in the intervals only 92.2% of the time. And we could
It's pretty magical.
keep going. So we have a much lower hit rate than we would hope to have if we were actually using z and sigma. Now, what's neat is if we use a t-table, notice this is getting much closer. And this is neat because with a t-table and something that we can actually get from the sample standard deviation, we're actually able to have a pretty close hit rate to what we would have if we actually knew the population standard.
I have a question. If we have enough confidence intervals, No, okay.
deviation. So that's the value of t and t statistics. And we're going to give more and more examples, including using a t-table in future videos. Flavia wanted to estimate the mean age of the faculty members at her large university. She took an SRS, or simple random sample, of 20 of the approximately 700 faculty members, and each faculty member in the sample provided Flavia with their age. The data were skewed to the right with a sample mean of 38.75. She's considering using her data to make a confidence interval to estimate the mean age of faculty members at her university. Which conditions for constructing a t-interval have been met? So pause this video and see if you can answer this on your own.
Okay, so like the Z interval needs to be random, needs to be independent. 20 of the approximately, yep, that's fine. That's like 3%. N equals less than 10% of the whole sample space. Okay. The data were skewed to the right, it's fine. Depends. Skewed. No. Random sample and the third.
Okay, now let's try to answer this together. Now, so original, so approximate. They say the data that we're getting in our sample is not symmetric, and the original distribution is unlikely to be normal. Think about it. It's not going to be, you're likely to have people who are, you could have faculty members who are 30 years older than this, 68 and 3/4, but you're very unlikely to have faculty members who are 30 years younger than this. And that's actually what's causing that skew to the right. So this one does not meet the normal condition. We can't feel good that our sampling distribution is equal to. So the main issue where our t interval might not be so good is that our sampling distribution
Give me a second. And I am back. I was gone for like 3 minutes. It's fine. Yep. Sample size. Yep. Methods. And then sample size again. Mm-hmm. Mm-hmm. Oh, I wish there was yes, okay. Standard deviation of what is what gives it is what gives it a new name. Mm-hmm. Okay, conditions. Is it random? It's random. Is it normal? Skewed to the right, but n is greater than 30. That's fine. Sampling distribution is probably going to be fine. Considered independent. N equals 20. I don't think that's enough. I don't think it's enough. Neither sample. Needs to be greater than 20, I think. Or greater than 30, maybe. Oops. Okay. Given a confidence level, we can take a critical value. Okay, it's pretty much the same thing. We look up t distribution. I don't know why it's called students t distribution. There's students t test as well. Whatever. Okay.
We are asked, what is the critical value T star or T asterisk for constructing a 98%?
98%. No, wait, okay, here. 98%. And our sample size is n equals 15. Here, 2.602. Or did we look at 99%? Let's see.
Confidence interval for mean here. Take that sample mean, and we're going to go plus or minus some margin of error. Now, in other videos, we have talked about that we want to use the t distribution here because we don't want to underestimate the margin of error. So it's going to be t star
Yes.
times the sample standard deviation divided by the square root of our sample size, which in this case was going to be 15, so the square root of n. But what they're asking us is, well, what is the appropriate critical value? What is the t star that we should use in this situation? And so we're about to look at a table, the different sample size versus of size, and it's 28%.
Oh, wait. Oh, right, okay. So n equals 15, 14, 2.624.
Confidence, our confidence level right away. That means you're leaving on, which is you can't set this level of t value. 264 is this choice. Or
98%. Okay. 2.998. 1498. 2.624. 1298. 2.681. No, that sucks. 2.718. No, 12. Oh, 13 degrees of freedom. 2.65. 1695. 2.12. Yeah, bonus question. N equals 20, so 19 degrees of freedom. 95%. 2.09. Yeah. Okay. Constructing a T interval, pretty easy.
A nutritionist wants to estimate the average caloric content.
So I think it's the same, right? So it's, well, we're doing with sample mean. Sample mean plus minus the star critical T value times the standard deviation of the mean of the sample mean, which is the square root of trying to remember what's above. So it's S minus something. Yeah, T interval calculation. Oh no, okay. Standard deviation over the square root of sample size. Oh wait, this is also for Z. Huh. What am I looking at? Yeah.
Of the burritos at a popular restaurant. They obtain a random sample of 14 burritos and measure their caloric content. Their sample data are roughly symmetric with a mean of 700 calories and a standard deviation of 50 calories. Based on this sample, which of the following is a 95% confidence interval for the mean caloric content of these burritos?
I just realized the confidence interval for a proportion versus a mean would be different because proportion is capped at 1. You can't have 110% proportion. That doesn't make sense. But a mean value could be negative, could be over 1. So that is why it's different. Okay. Some things like that you don't need a math textbook to tell you. It's just nice when you figure these things out on your own, you know? For proportion, and then they probably both use Z. Okay, so that's, wait, proportion. Nope. Mm-hmm. Mm-hmm.
So pause this video and see if you can figure it out. All right, what's going on here? So there's a population of burritos here. There is a mean caloric content that the nutritionist wants to figure out, but doesn't know the true population parameter here, the population mean. And so they take a sample of 14 burritos and they calculate some sample statistics. They calculate the sample mean, which is 700. They also calculate the sample standard deviation, which is equal to 50. And they want to use this data to construct a 95% confidence interval. And so our confidence interval is going to take the form, and we've seen this before, our sample mean plus or minus our critical value
Times sample standard deviation over the square root of n.
times the sample standard deviation divided by the square root of n. The reason why we're using a t-statistic is because we don't know the actual standard deviation for the population. If we knew the standard deviation for the population, we would use that instead of our sample standard deviation. And if we use that, if we used sigma, which is a population parameter, then we could use a z statistic right over here. We would use a z distribution. But since we're using this sample standard deviation, that's why we're using a t-statistic. But now let's do that. So what is this going to be? So our sample mean is 700. They tell us that. So it's going to be 700 plus or minus. So what would be our critical value for a 95% confidence interval? Well, we will just get out our t-table. And with a t-table, remember, you have to care about degrees of freedom. And if our sample size is 14, then that means you take 14 minus 1. So degrees of freedom is n minus 1. So that's going to be 14 minus 1. So 1 is 0.5%. So that is this 0. It's going to be 2 standard deviation. root part is.
I see. Yeah. This is just warm-ups, by the way, guys. Like, I know this stuff already, but it's nice just to go over it again. It doesn't hurt, you know. We have so many hours in a day, so many hours in a week, that to stop and review, it's not a bad thing. Based on the sample, which is the following, okay, 99%. Degrees of freedom, 11 minus 1, 10, 99%, 3.169. It's this one or this one. Uh, N. So obviously this is mean, sample mean. This is T star times standard error. Well, we can just say, yeah, standard error. Why am I giving it a star? Standard error. Yeah, like that. And now everything's blue, damn it. Okay. 14 burritos, DF. 15. Why am I writing this out? I can calculate this stuff in my head. 30 and oh no, it does make sense. Okay, so 50 over square root of 13 times 13, 95, 2.16 times 2.16, 29, and all of them are wrong. Oh, wait. This is supposed to be 14. I used degrees of freedom. 28.86, 28.9. 95, 6, 2.447, okay, 2.447, it's T star times, it's freaking out. Okay, there you go. Oh, why is it doing that? Let's write out every variable of the problem just for this. Okay, so n equals 16, sample standard deviation equals and x bar, which is sample mean equals Yeah. I think that's about it. And then if we just uh change color again, calculator. So this one. Paired data. Confidence interval for a mean with paired data. Okay, let's see what it says.
Point. A group of friends wondered how much faster they could snap their fingers on one hand versus the other hand. Very important question in life. Each person snapped their fingers with their dominant hand for 10 seconds and their non-dominant hand for 10 seconds. Where if you're right-handed, right hand would be your dominant hand. If you were left-handed, left hand would be your dominant hand. Each participant flipped a coin to determine which hand they would use first. Because if you always used your dominant hand first, maybe you're tired by the time you're doing your non-dominant hand or there's something else. So here, it's random which one you use first. Here are the data for how many snaps they performed with each hand, the difference for each participant, and summary statistics. And this is actually real data from the Khan Academy content team. And so you see for each of the participants, for Jeff right over here, he was able to do 44 snaps in 10 seconds on his dominant hand, which is impressive, more than I think I could do. And he was even able to do 35 on his non-dominant hand. And so the difference here, the dominant hand minus the non-dominant, was 9. And then they tabulated this data for all 5 members. Now they also calculated summary statistics for them. But this is the really interesting thing right over here. This is the difference between the dominant and the non-dominant hand.
How do you?
And so what they did here, the mean difference, what they did is they took this row right over here, and they calculated the mean, which they got to be 6.8. And then they calculated the standard deviation of these differences right over here, which they got to be approximately 1.64. And then we are asked, create and interpret a 95% confidence interval for mean difference in number of snaps for these participants. So pause this video, see if you can make some headway here. See if you can think about how to...
Uh, so you have two distributions. They're both distributed some way or another, you know. And you get the difference in the mean, you get the difference in standard deviation, and then you result in a new frickin' distribution, and then you basically just generate a confidence interval for that. For standard deviation, the difference is, I think it's like you add the two, then you square the two. Don't quote me on that, but let's see. Okay, 1.64 squared. I'm wrong. I'm wrong again. I keep forgetting how to do this, but you add, you square root. Standard. You square, you add, then you square root. Let's see. Okay. 2.65 squared. And I'm wrong again.
Approach this. So what's interesting here is we're not trying to construct a confidence interval for
Hmm. Okay, hold on. Let's keep playing around. Because this is something I keep getting wrong.
just the
Well, let's just ask AI. It's taking too long. What the fuck is that?
mean number of snaps for the
Oh my god, that's not what I was asking for. Dumbass.
dominant hand, or the mean number of snaps for the non-dominant hand. We're constructing a 95% confidence interval for a mean difference. Now, you might say, wait, I have two different samples here, and then this third sample is, or this third data is somehow constructed from these other two. But one way to think about it, this is matched pairs design. So in a matched pairs design, what you do is, for each participant, for each member in your sample, you will make them do the control and the treatment. So for example, you could do the control as how many they can do in the dominant hand in 10 seconds, and the treatment is how many they can do in the non-dominant hand. And in matched pairs design, you're really concerned about the difference. And so what you can really view this as is you just have one sample size of 5 for which you are calculating the difference for each member of that sample and the standard deviation across that entire sample. Now, before we calculate the confidence interval, let's just remind ourselves some of our conditions that we like to think about when we are constructing confidence intervals. The first condition we think about is whether our sample is random. Now, if we were trying to make some type of judgment about all human beings and their snapping ability, this would not be a random sample. These people all work
Okay,
at
I'm low-key annoyed. I keep forgetting. Fuck. Am I tripping? What the fuck? Doesn't make sense. How is it 1.6?
Khan Academy. Maybe somehow in our interview process, we select for people who snap particularly well. But whatever inferences we make, we can say, hey, this is roughly true about this group of friends. Now, the next condition we want to think about is the normal condition. Now, there's a couple of ways to think about it. If we had sample size of 30 or larger, the central limit theorem says, okay, the distribution, the sampling distribution would be roughly normal. The sampling distribution is 5 different. We could study, and it's the sum of many, many processes. Those things, this is a fun thing for friends to do. The difference here, the dominant hand calculated the mean, which they got, did here, the
Ah, I'm a dickhead. Okay.
mean difference. What they did is they took this row right over here, and they calculated the mean, which they got to be 6.8, number of snaps for the dominant hand, or the mean number of snaps for the non-dominant hand. We're constructing a 95% confidence interval for a mean difference. Now, you might say, wait, I have two different samples here, and then this third sample.
I was busy chasing ghosts.
And study when you think about biological processes, like how well someone snaps, which is the product of a lot of things happening in a human body, and it's the sum of many, many processes. Those things also tend to have a roughly normal distribution, but I won't go into too much depth there. But all of these things, once again, this isn't a super robust study, but this is a fun thing for friends to do if they have nothing else to do. All right. Now, the third one is independence. And this one actually we can feel pretty good about because Jeff's difference right over here really shouldn't impact David's difference, or David's difference really shouldn't impact Kim's difference, especially if they're not observing each other. Let's just say, for sake of argument, that they did it all independently in a closed room with an independent observer, so they weren't trying to get competitive or something like that. But needless to say, this isn't super robust study, but we can still calculate a 95% confidence interval. So how do we do that? Well, we've done this so many times. Our confidence interval would be our sample mean, so it would be the mean of our difference, plus or minus. Now, we don't know the population standard deviation, so we're going to use our sample standard deviation. And if you're using a sample standard deviation, and this confidence interval is all about the mean, and so our critical value here is going to be based on a t-table, on a t-statistic, and they're going to multiply that times the sample standard deviation of the differences, divided by the square root of our sample size, divided by the square root of 5. Now, we know most of this data here. And let me just write it down over here. We know the mean, the sample mean right over here is 6.8. So it's going to be 6.8 plus or minus. And now, what will be our critical value here? Well, we want to have a 95% confidence interval. And what's our degrees of freedom? Well, it's 1 less than our sample size. So our degrees of freedom right over here is equal to 4. And so we're ready to use a t-table. So this is a truncated. whether our sample is random. Now, if we were trying to make some type of judgment about all human beings and their snapping ability, this would not be a random sample. These people all work at Khan Academy. Maybe somehow in our interview process, we select for people who snap particularly well. But whatever inferences we make, we can say, hey, this is roughly true about this group of friends. Now, the next condition we want to think about is the normal condition. Now, there's a couple of ways to think about it. If we had sample size of 30 or larger, the central limit theorem says, okay, the distribution, the sampling distribution would be roughly normal, the sampling distribution of the sample means. But obviously, our sample size is much smaller than that. One way to think about it, we could just plot our data points and see whether they seem to be skewed in any way. And if we just do a little dot plot right over here, we could say, let's say make this 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have one data point where the difference was 9, one data point where the difference is 5, one data point where the difference is 8, one data point where the difference is 6, and another data point where the difference is 6. And so this doesn't look massively skewed in any way. Our mean difference was right over here, is about 6.8. It looks roughly symmetric. So we can feel okay about this normal distribution. This isn't the best study that one could conduct. This is obviously a small sample size. It's not random of the entire population, but maybe we could go with it. Also, when you think about biological processes, like how well someone snaps, which is a product of a lot of things happening in a human body, and it's the sum of many, many processes, those things also tend to have a roughly normal distribution. But I won't go into too much depth there. But all of these things, once again, this isn't a super robust study, but this is a fun thing for friends to do if they have nothing else to do. All right. Now, the third one is independence. And this one actually we can feel pretty good about because Jeff's difference right over here really shouldn't impact David's difference, or David's difference really shouldn't impact Kim's difference, especially if they're not observing each other. Let's just say, for sake of argument, that they did it all independently in a closed room with an independent observer, so they weren't trying to get competitive or something like that. But needless to say, this isn't super robust study, but we can still calculate a 95% confidence interval. So how do we do that? Well, we've done this so many times. Our confidence interval would be our sample mean, so it would be the mean of our difference, plus or minus. Now, we don't know the population standard deviation, so we're going to use our sample standard deviation. And if you're using a sample standard deviation, and this confidence interval is all about the mean, and so our critical value here is going to be based on a t-table, on a t-statistic, and then we're going to multiply that times the sample standard deviation of the differences, divided by the square root of our sample size, divided by the square root of 5. Now, we know most of this data here. Let me just write it down over here. We know the mean, the sample mean right over here is 6.8, so it's going to be 6.8 plus or minus. And now, what will be our critical value here? Well, we want to have a 95% confidence interval. And what's our degrees of freedom? Well, it's 1 less than our sample size, so our degrees of freedom right over here is equal to 4. And so we're ready to use a t-table. So this is a truncated t-table that I could fit on my screen here. And so there's a couple of ways to think about it. Here they actually give us the confidence level. And the reason why that corresponds to a tail probability of 0.025 is if you take the middle 95% of a distribution, you're going to have 2.5% on either end. That's going to be your tail probability. So that's all that's going on over there. So we're going to freedom. So sample, as I already wrote over here, 0.8 was equally the mean number of snaps. Since 0
Oops. Oh my God. No. Oh, there you go. No. Ah, yes. Okay, that makes sense. I wasn't reading. 400 is contained within the. Hmm. So is almost certainly below. What? It's potentially above. Interesting. Wait. Ah, I see. Okay. It's weird. Okay. Sometimes it talks about the outside or the inside and double negatives and yeah, okay. No more than 2 hours. Okay. It's almost definitely because it's 95%, right? So 95% of the confidence intervals would be above 120, roughly. Don't meet the specification. Sure, okay. 15, it's this or this. Okay.
That's mu right over there. A quality controlled expert at a drink bottling factory took a random sample of bottles from a batch and measured the amount of liquid in each bottle in the sample. The amount in the sample had a mean of 503 milliliters and a standard deviation of 5 milliliters. They want to test if this is convincing evidence that the mean amount for bottles in this batch is different than the target value of 500 milliliters. Let mu be the mean amount of liquid in each bottle in the batch. Write an appropriate set of hypotheses for their significance test, for the significance test that the quality control expert is running. So pause this video and see if you can do that. All right, now let's do this together. So first, you're going to have two hypotheses. You're going to have your null hypothesis and your alternative hypothesis. Your null hypothesis is going to be a hypothesis about the population parameter that you care about, and it's going to assume kind of the status quo, no news here. And so the parameter that we care about is the mean amount.
Hey, let's see. Yep. So this is just a null and null, null and alternative hypothesis test. Null, no difference. Alternative, there is difference. What kind of difference? That's up to the question. So a mean amount for the bottles is different. So that's either or,
of liquid in the
two-tailed
bottles in the
test,
batch. So that's mu right over there.
two-sided
And what would be the
test.
assumption? It's what the parameters, this 500, this told a set of hypotheses. This would be
Yeah.
our null hypothesis. And then our alternative hypothesis.
Okay, next. Warmer, so higher.
Sunil and his friends have been using a group messaging app for over a year to chat with each other. He suspects that, on average, they send each other more than 100 messages per day. Sunil takes a random sample of 7 days from their chat history and records how many messages were sent on those days. The sample data are strongly skewed to the right, with a mean of 125 messages and a standard deviation of 44 messages. He wants to use these sample data to conduct a t-test about the mean. Which conditions for performing this type of significance test have been met? So let's just think about what's going on here. Sunil.
So t-test, like a z-test, is one in which you just get the probability, you get the area under a curve, maybe under a range, definitely under a range of values, and you see if it falls below the value of alpha you set beforehand. Pretty easy.
Might have some type of a null hypothesis. Maybe he got this 100, maybe he read a magazine article that says that on average, the average teenager sends 100 text messages per day. And so maybe the null hypothesis is that the mean amount of messages per day that he and his friends send, which was signified by mu, maybe the null is 100, that they're no different than all other teenagers. And maybe he suspects, and actually they say it right over here, his alternative hypothesis would be what he suspects, that they'd send more than 100 text messages per day. And so what he does is he takes a sample from the population of days, and there's over 365. They say they've been using the group messaging app for over a year, and he takes 7 of those days. So n is equal to 7. And from that, he calculates sample statistics. He calculates the sample mean, which is trying to estimate the true population mean right over here. And he also is able to calculate a sample standard deviation. And what you do in a significance test is you say, well, what is the probability of getting this sample mean, or something even more extreme, assuming the null hypothesis? And if that probability is below a preset threshold, then you would reject the null hypothesis and it would suggest the alternative. But in order to feel good about that significance test and be able to even calculate that p-value with confidence, there are conditions for performing this type of significance test. The first is that this is truly a random sample. And that's known as the random condition. And you have seen this before when we did significance tests with proportions. Here we're doing it with means. Population mean, sample mean. In the past we did it with population proportion and sample proportion. Well, the random condition, it says it right here. Sunil takes a random sample of 7 days from their chat history. They don't say how he did it, but we'll just take their word for it, that it was a random sample. The next condition is sometimes known as the independence condition. And that's that the individual observations in our sample are, they don't say another way where you could feel that it's rough. The population of days, 7, will feel good that the sampling distribution of the sample means right over here is approximately normal. And this is going to be a little bit different than what we saw with significance tests when we dealt with proportions. There's a few ways to feel good that the sampling distribution of the sample means is normal. One is if the underlying parent population normal. So parent population normal. Now, the normal way that we could feel good that our sampling sample data are strongly skewed to the right. It's clearly not a.
Yep. Okay. Both. Random sample. Um, Random, independent.
What I want to do in this video is give a primer on thinking about when to use a z statistic versus a t statistic.
Use t-statistic when sample sizes are smaller, but also every time the population standard deviation is not known.
When we are doing significance tests. So there's two major scenarios that we will see in an introductory statistics class. One is when we are dealing with proportions. So I'll write that on the left side right over here. And the other is when we are dealing with means. In the proportion case, when we are dealing with proportions, introductory statistics class. One is when we are dealing with proportions. So I'll write that on the left side right over here. And the other is when we are dealing with means. In the proportion case, when we're doing our significance test, we will set up some null hypothesis that usually deals with the population proportion. We might say it is equal to some value. Let's just call that p sub 1. And then maybe you have an alternative hypothesis that, well, no, the population proportion is greater than that, or less than that, or it's just not equal to that. So let me just go with that one. It's not equal to p sub 1. And then what we do to actually do the significance test, is we take a sample from the population. It's going to have a sample size of n. We need to make sure that we feel good about making the inference. We've talked about the conditions for inference in previous videos multiple times. But from this, we calculate the sample proportion. And then from this, we calculate the p-value. And the way that we do the p-value, remember, the p-value is the probability of getting a sample proportion at least this extreme. And if it's below some threshold, we reject the null hypothesis, and it suggests the alternative. And over here, the way we do that is, well, we find an associated z value for that p, for that sample proportion. And the way that we calculate it, we say, okay, look, our z is going to be how many of the sampling distribution's standard deviations are we away from the mean. And remember, the mean of the sampling distribution is going to be the population proportion. So here, we got this sample statistic, this sample proportion. The difference between that and the assumed proportion. Remember, when we do these significance tests, we try to figure out the probability assuming the null hypothesis is true. And so when we see this p sub 0, this is the assumed proportion from the null hypothesis. So that's the difference between these two, the sample proportion and the assumed proportion. And then you'd want to divide it by what's often known as the standard error of the statistic, which is just the standard deviation of the sampling distribution of the sample proportion. And this works out well for proportions, because in proportions, I can figure out what this is. This is going to be equal to the square root of the assumed population proportion times 1 minus the assumed population.
Wait, hold up. Okay. Z. Number of standard deviations. P hat. Sample probability. Sample probability. Sample proportion probability. It's kind of the same thing. Sample proportion, the difference to the null hypothesis over sample standard deviation.
Proportion, all of that over n. And then I would use this z statistic to figure out the p-value. And in this case, I would look at both tails of the distribution because I care about how far I am either above or below the assumed population proportion. Now with means, there's definitely some similarities here. You will make a null hypothesis. Maybe you assume the population mean is equal to mu1. And then there's going to be an alternative hypothesis that maybe your population mean is not equal to mu1. And you're going to do something very simple. You take your population, take a sample of size n, and instead of calculating a sample proportion, you calculate a sample mean. And actually you can calculate other things like a sample standard deviation. But now you have an issue. You say, well, ideally I would use a z statistic, and you could if you were able to say, well, I could take the difference between my sample mean and the assumed mean in the null hypothesis, so that would be this right over here. That's what that 0 means, the assumed mean from the null hypothesis. And I would then divide by the standard error of the mean, which is another way of saying the standard deviation of the sampling distribution of the sample mean. But this is not so easy to figure out. In order to figure out this is going to be the standard deviation of the underlying population divided by the square root of n. We know what n is going to be if we conducted the sample, but we don't know what the standard deviation is. So instead, what we do is we estimate this. And so we'll take the sample mean, we subtract from that the assumed population mean from the null hypothesis, and we divide by an estimate of this, which is going to be our sample standard deviation divided by the square root of n. But because this is an estimate, we actually get a better result. Instead of saying, hey, this is an estimate of our z statistic, we will call this our t statistic. And as we'll see, we'll then look this up in a t table, and this will give us a better sense of the probability. What we do is we estimate this. And so we'll take the sample mean, we subtract from that the assumed population mean from the null hypothesis, and we divide
But
by an estimate of this. Well, I could take the difference assumed population proportion, the statistic, and this will give us a better sense. Our standard deviation is. So instead, what we do is we estimate this. And so we'll take the sample mean, we subtract from that the assumed population mean from the null hypothesis, and we divide by an estimate of this, which is going to be our sample standard deviation divided by the square root of n. But because this is an estimate, we actually get a better result. Instead of saying, hey, this is an estimate of our z statistic, we will call this our t statistic. And as we'll see, we'll then look this up in a Rory suspects that teachers in his school district have less than 5 years of experience on average. He decides to test. His null hypothesis is that the mean number of years of experience is 5 years, and his alternative hypothesis is that the true mean years of experience is less than 5 years, using a sample of 25 teachers. His sample mean was 4 years, and his sample standard deviation was 2 years. Rory wants to use these sample data to conduct a t-test on the mean. Assume that all conditions for inference have been met. Calculate the test statistic for Rory's test. So I always just like to remind ourselves what's going on. So you have your null hypothesis here, that the mean number of years of experience for teachers in the district is 5. And then the alternative hypothesis is that the mean years of experience is less than 5 for teachers in the district. So if this represents all the teachers in the district, the population, then what he did is he took a sample, and it said he used a sample of 25 teachers. So n here is equal to 25. And then from that sample, he was able to calculate some statistics. He was able to calculate the sample mean. So that sample mean was 4 years. The sample mean was 4 years. And then he was also able to calculate the sample standard deviation. The sample standard deviation was equal to 2 years. Now, the whole point that we do, or the main thing we do when we do significance tests, is we say, all right, if we assume the null hypothesis is true, what's the probability of getting a sample mean this low or lower? And if that probability is below a preset significance level, then we reject the null hypothesis and it suggests the alternative. But in order to figure out that probability, we need to figure out a test statistic. Sometimes we use a z-test if we're dealing with
that's gonna look something like t equals, yep, and the difference between sample mean minus the null hypothesis over S, which is that.
with proportions. You would divide by the standard deviation of our assumed population mean, the population parameter of our statistic. Well, this is going to be equal to, let's see, our sample mean is 4 to is then look this t value up on a t table. We are negative 2.5 is and between for observations, and he feels good that the sampling distribution is going to be roughly normal, and we've talked about that in other videos. Rory suspects that maybe he observed either with replacement or it's less than 10% of the population, and he feels good that the sampling distribution is going to be roughly normal, and we've talked about that in other videos. Rory suspects his suspicion that the mean, and what we would do in this, what Rory would do, is then look this t value up on a t table, and say, so if you look at a distribution of a t statistic, something
Hmm. Did it not do it right? Whoa. Okay, so interesting. Okay. Okay, I do not have a
Miriam was.
calculator, so we
So if
will
we think
skip
about a t
this.
distribution, I'll try to hand draw. All we have to do,
It's fine.
Katerina was testing her null hypothesis is that the true population mean of some data set is equal to 0, versus her alternative hypothesis is that it's not equal to 0. And then she takes a sample of 6 observations, and then using that sample, her test statistic, I can never say that, her test statistic was t is equal to 2.75. Assume that the conditions for inference were met. What is the approximate p-value for Katerina's test? So like always, pause this video and see if you can figure it out. Well, I just always like to remind ourselves what's going on here. So there's some population here. She has a null hypothesis that the mean is equal to 0, but the alternative is that it's not equal to 0. She wants to test her null hypothesis, so she takes a sample size, or she takes a sample of size 6. From that, since we care about the population parameter we care about is the population mean, she would calculate the sample mean in order to estimate that, and the sample standard deviation. And then from that, we can calculate this t-value. The t-value is going to be equal to the difference between her sample mean and the assumed population mean from the null hypothesis. That's what this little sub-zero means. It means it's the assumed mean from the null hypothesis divided by our estimate of the standard deviation of the sampling distribution. I say estimate because unlike when we were dealing with proportions we can actually calculate the assumed, based on the null hypothesis, sampling distribution standard deviation. But here we have to estimate it. And so it's going to be our sample standard deviation divided by the square root of n. Now, in this example, they calculated all of this for us. They said, hey, this is going to be equal to 2.75. And so we can just use that to figure out our p-value. But let's just think about what that is asking us to do. So the null hypothesis is that the mean is 0. The alternative is that it is not equal to 0. So this is a situation where, if we're looking at the t distribution right over here, it's my quick drawing of a t distribution. If this is the mean of our t distribution, what we care about is things that are at least 2.75 above the mean and at least 2.75 below the mean, because we care about things that are different from the mean, not just things that are greater than the mean or less than the mean. So we would say, well, what's the probability of getting a t value that is more 2.75 or more, or 2.75 or more below the mean? This is negative 2.75 right over there. So what we have here is a t-table, and a t-table is a little bit different than a z-table because there's several things going on. First of all, you have your degrees of fun is 5, and so we are going to be in this row right over here, 2.75 on this row. And we see 2.75, it's a little bit less than that, but that's the closest value. It's a good bit more than this right over here, but it's a little bit closer to this value than this value. And so our tail probability, remember, this is only giving us this probability right 0 direction because we are less than the t-distribution symmetric. This is going to be approximately 0.02. And so our p-value, which is going to be the probability of getting a t-value that is at least 2, the p-value. And then, of course, Katerina would want to compare that alternative to her significance level that she set ahead of time. And if this
2.411. Okay. And it's greater than t-test. 2.41187. 2.411. What? It's definitely between 0.05 and 0.02. Yeah. Negative 2.83. DF8. So confusing. Frick. Negative 2.83 is somewhere here. That's cumulative probability, but it's negative. Okay. That's the probability over there. One tail, 0.01. Maybe it's the same as well. Ah, Christ, I don't know. Less than. I'm gonna just guess here. I need a calculator to do this.
Jude was curious if the automated machine at his restaurant was filling drinks with the proper amount. He filled a sample of 20 drinks to test his null hypothesis, which is the actual population mean for how much drink there was in the drinks per drink is 530 milliliters, versus his alternative hypothesis is that the population mean is not 530 milliliters, where mu is the mean filling amount. The drinks in the sample contained a mean amount of 528 milliliters with a standard deviation of 4 milliliters. These results produced a test statistic of t is equal to negative 2.236 and a p-value of approximately 0.038. Assuming the conditions for inference were met, what is an appropriate conclusion at the alpha equals 0.05 significance level? And they give us some choices here. And like always, I encourage you to pause this video and see if you can figure it out on your own. All right, so now let's work through this together. So let's just remind ourselves what's going on. So you have some population of drinks, and we care about the true population mean. You have a null hypothesis around it that the true mean is 530 milliliters, but then there's the alternative hypothesis that it's not 530 milliliters. So to test your null hypothesis, you take a sample. In this case, we had a sample of 20 drinks, and using that sample, you calculate a sample mean, and then you also calculate a sample standard deviation. They tell us these things right over here. And then using this information, and actually our sample size, you are able to calculate a t-statistic. You're able to calculate a t-statistic, and then using that t-statistic, you are able to calculate a p-value. And the p-value is, what is the probability of getting a result at least this extreme if we assume that the null hypothesis is true? And if that probability is lower than our significance level, then we say, hey, that's a very low probability. We're going to reject our null hypothesis, which would suggest our alternative. So the key to this question is just to compare this p-value right over here to our significance level. And as we see, the p-value 0.038 is indeed less than 0.05.
Wait.
And so because of this, we would reject the null hypothesis, 530 milliliters. So this is rejecting the null hypothesis. It was lower than our significance.
Yeah, sure. Okay.
Regulations require that product labels on containers of food that are available for sale to the public accurately state the amount of food in those containers. Specifically, if milk containers are labeled to have 128 fluid ounces and the mean number of fluid ounces of milk in the containers is at least 128, the milk processor is considered to be in compliance with the regulations. The filling machines can be set to the labeled amount. Variability in the filling process causes the actual contents of milk containers to be normally distributed. A random sample of 12 containers of milk was drawn from the milk processing line in a plant, and the amount of milk in each container was recorded. The sample mean and standard deviation of this sample of 12 containers of milk were 127.2 ounces and 2.1 ounces respectively. Is there sufficient evidence to conclude that the packaging plant is not in compliance with the regulations? Provide statistical justification for your answer. So pause this video and see if you can have a go at it. All right, now let's do this together. So first, let's
Okay, let's see. You would first set up the null and alternative hypothesis, or you would draw the problem. So your null hypothesis is 128 fluid ounces at least, and conclude that the packaging plant is not in compliance. So two-tailed t-test. And we're doing a t-test because, oops, we don't know the population standard deviation or variance. So From there, you would just do a simple student's t-test. The degrees of freedom would be 11, and it'd be t equals the difference between this and that, so negative 0.08 over 12 divided by, no, 2.1 divided by the square root of 12. I should have looked at the conditions for inference. Inference basically just means to safely assume or reasonably assume. Yeah, okay. And then it was not in compliance, so it's too low.
Talking about. So we just another food that
Alpha, okay, fail to reject, not enough evidence. Longer than 2 hours. I hate these ones so much. Negative 2.77, okay. Somewhere here. Is below? Yeah, below. Okay. Something right below 2.896. 0.01. Hmm. Yeah, let's do it. Eh, damn. Oh wait, this one is also right below it. Oh, nope. Why? T-test, short calculator. Sure, okay. Do the denominator first. So standard deviation 6 divided by 4. Difference is -3, -2. Neither. You joking? What? No way. Less than. More, greater than. How's 0.1? Huh? Ah, that's dumb. Okay. Cumulative probability is actually what's on top. Okay, it's fine. 1.9 is less than 1.9. I'm gonna fuck it up again. Oh my fucking god. Zero point zero five. Fuck's sakes. It's going less here. So 0.05, less than 0.05 or greater. Fuck no. Dumb. Okay, again. Where the shit did my fucking. Okay. Negative 1.79. Here, roughly. Somewhere here. Two tails. 0.1. I don't want to say it's slightly less. Slightly less. Okay, so on the left. Wait. Cumulative probability. So up until here. P-value is greater than 0.01, right? Less than? Oh, wait, hold on. No, okay. 2.44. Isn't this just the same? What? What? Wait, what? No, no, it's not. Fuck. Yeah. 8, negative 2.8. Here, what type of test is it? Less than 52. It's negative, that's fine. Um, 0.01 and 2.83 towards the side. Less than 0.01. Sure. Good enough. Okay. Time check. 15 minutes. Okay.
A food scientist wants to estimate the difference between the mean weights of eggs classified as jumbo and large. They plan on taking a sample of each type of egg to construct a two-sample t-interval. Which of the following are conditions for this type of interval? So before I even look at these choices, and they say choose all answers that apply, so it might be more than one, let's just think about what the conditions for inference for this type of interval actually are. So we've done this many times in many different contexts. And so we first of all have the random condition. And that's the idea that each of our samples are random, or we are conducting some type of an experiment where we randomly assign folks to one, or eggs in this case, to one of two groups. In this case, we are taking two samples, and we would hope that they are truly random samples. The second is the normal condition. And the normal condition is a little bit different depending on whether we're talking about means or whether we're talking about proportions. The random condition is essentially the same. The normal condition when we're talking about means, remember, they're looking at the difference between mean weights of eggs, is you would want there's actually several ways to meet the normal condition. One is if the underlying distribution is normal. The second way is if your sample sizes for each of your samples are greater than or equal to 30. So if your first sample size is greater than or equal to 30, and your second sample size is greater than or equal to 30. Or even if the underlying data, you don't know whether it's normal or if it isn't normal, and even if you aren't able to meet these, as long as your sample data is roughly symmetric and not skewed heavily in one way or the other, then that also roughly meets the normal condition when we're dealing with means. And then the third condition, and we see this whether we're dealing with means or proportions or differences of means or differences of proportions, is the independence condition. And this is the idea that either your individual observations are done with replacement in both of your samples, or that the sample size for both of your samples is no more than 10% of the population, then you have met this condition. So with that little bit of a review, let's see which of these apply. They observe at least 10 heavy eggs and 10 light eggs in each sample. So this actually is the normal condition when we are dealing with proportions, not for means. So I would rule this out. It's a good distractor choice. The eggs in each sample are randomly selected from their population. Yep, that's the random condition right over there. So I would select that. they sample an equal number of each type of egg. So this is a common misconception that whether we're dealing with means or proportions, when we're thinking about the difference between, say, means or the difference between proportions, that somehow your sample sizes have to be the exact same. That is not the case. Your sample sizes do not have to be the exact case, or do not have to be the exact same. So we would rule this out as well. So right over here, they have listed the random condition. They could have also listed the normal condition and the independence condition. A food scientist wants to
Oh yeah, oh damn. It was just one. But it doesn't say how many people there are. What the hell? A group of researchers want to estimate the difference time it takes to heal enough to return to work after knee replacement surgery. Yeah, it doesn't say how many people there are. Oh wait, no, it does. Oh my God. Why would they put it there? Ah, fuck sakes.
scientist wants to estimate the difference between the mean weights of eggs classified as jumbo and large. They plan on taking a sample of each type of egg to construct a two-sample t interval. which of the following are conditions for this type of interval. So before I even look at these choices, and they say choose all answers that apply, so it might be more than one, let's just think about what the conditions for inference for this type of interval actually are. So we've done this many times in many different contexts. And so we first of all have the random condition. And that's the idea that each of our samples are random, or we are conducting some type of an experiment where we randomly assign folks to one, or eggs in this case, to one of two groups. In this case, we are taking two samples, and we would hope that they are truly random samples. The second is the normal condition. And the normal condition is a little bit different depending on whether we're talking about means or whether we're talking about proportions. The random condition is essentially the same. The normal condition when we're talking about means, remember, they're looking at the difference between mean weights of eggs, is you would want there's actually several ways to meet the normal condition. One is if the underlying distribution is normal. The second way is if your sample sizes for each of your samples are greater than or equal to 30. So if your first sample size is greater than or equal to 30 and your second sample size is greater than or equal to 30. Or even if the underlying data, you don't know whether it's normal or if it isn't normal. And even if you aren't able to meet these, as long as your sample data is roughly symmetric and not skewed heavily in one way or the other, then that also roughly meets the normal condition when we're dealing with means. And then the third condition, and we see this whether we're dealing with means or proportions or differences of means or differences of proportions, is the independence condition. And this is the idea that either your individual observations are done with replacement in both of your samples, or that the sample size for both of your samples is no more than 10% of the population, then you have met this condition. So with that little bit of a review, let's see which of these apply. They observe at least 10 heavy eggs and 10 light eggs in each sample. So this actually is the normal condition when we are dealing with proportions, not for means. So I would rule this out. It's a good distractor choice.
Wow.
The eggs in each sample are randomly selected from their population. Yep, that's the random condition right over there. So I would select that. They sample an equal number of each type of egg. So this is a common misconception that whether we're dealing with means or proportions, when we're thinking about the difference between, say, means or the difference between proportions, that somehow your sample sizes have to be the exact same. That is not the case. Your sample sizes do not have to be the exact case, or do not have to be the exact same. Right over to the normal condition.
What? It's fine. I'm kind of cooked anyways. Like 5 minutes left. Okay, let's quickly wrap up, I guess. We have, oh, jeez, I almost killed the computer. Okay. Whoops. So we looked here at confidence intervals again, and we remember what they are. You draw a sample, or well, you generate a confidence interval based on the sample that you have, and you draw a sample from a from a population, and basically with the confidence interval, if you set it up right and all of the conditions for setting up the confidence interval are met, and you use the right confidence interval Z or T, you'll end up every time you draw samples and generate confidence intervals, which is just a static formula, but samples change. You'll be capturing the population parameter that you're trying to estimate for. Um, Hopefully the percentage of your confidence level if you set it up right. And for the population mean, it's slightly different to the population proportion because the mean can take pretty much any value, whereas a proportion is confined into a value between 0 and 1. And then we looked at t-tests for the population mean. Pretty straightforward. It's like a z-table, but you use degrees of freedom instead. And I'm still wrapping my head around how to interpret it with a negative z t-score, positive t-score, if it's greater or less than. It looked like you never do 1 minus, so that's kind of interesting. Okay, carrying out a test. Yep, we looked at getting the difference and doing students paired t-test. So, getting the difference between paired data. Is that right? Maybe not paired data. There's paired data, there's independent data. I'm so tired, guys. But I still got the math done. I've been slacking on it, so I'm really happy that I got this done. From quality control to predicting the amount of snowfall that will result from an upcoming blizzard, this unit will give you the tools to calculate an inference from a population mean to make predictions about quantitative outcomes. So if you like this video, leave a like, comment, subscribe if you aren't already, just so that you can see me bothering you in your news feed. And I will see you in the next video. Peace.